Hi kids, we left off here the other day when we learned how to convert particles into moles and then moles into particles. We know that this number, Avogadro's number, also called avocado's number or the guacamole number, that is a huge number, 6.02 times 10 to the 23rd, and it is used to group these massive numbers into something that's more easily understandable. So the idea of a mole is sort of like a dozen, only a heck of a lot bigger than 12. So we're going to pick up from there today, and we're going to learn how to change masses into moles, because we never really actually count the things in chemistry. It's not possible in almost any circumstances to do that, and so the way that we usually measure things in chemistry is by measuring their mass. So let's get into this. So mass to mole calculations. Based on the lab work that you have done just in the last couple of days, we should have figured out that there is a thing called a molar mass or a formula weight. It's used, both of those names are sort of synonymous. They mean the weight or the mass of a mole of an element or of a compound. And so the way that this works is, if you look on your periodic table, the average atomic mass on the elements square in your table is the same thing as what's called the molar mass or the formula weight. So I grabbed a whiteboard here. If we looked at sodium square, we would see that sodium is element number 11. Now it's element number 11 because it has 11 protons. The average mass is 22.98977. The reason it's an average and the reason it's such a number so close to 23 but not really 23 is we're talking about isotopes. Remember that there's different isotopes of a lot of these different elements. And so if we average out based on the number of isotopes and the weights of the isotopes and how the relative abundance of those isotopes works out in the universe, we find that average. In any case, so there's no sodium atom in the universe that has got a mass of 22.98977, but that is the average mass of all of the sodium atoms in the universe. And so that's an interesting number right there. It tells me the mass of a single atom in something called atomic mass units, AMUs. So a single sodium atom has got a mass of 22.98977 AMUs. It also tells me the mass of a whole mole of those things. It is the molar mass of sodium as well. And the units then aren't AMUs, they would be grams. So 22.98977 grams of sodium is 1 mole of sodium. It's the molar mass. So if you look on your periodic table, quickly just try and follow along here. So zinc, you should look at zinc and find that zinc as element number 29, I think, no, element 30, and it is going to have a molar mass of 65.38 grams or thereabouts. Different periodic tables give different levels of precision in those numbers, and so it should be, very within a very, very small amount of that number. Carbon is 12.011, so you get the idea. Now, for elements, that's one thing. We just look up their molar masses on the periodic table. What if we had something like salt or like sugar? Well, hopefully in your lab work you found that when we had water, the way we found the mass of a mole of water is we added up the mass of 2 hydrogens and 1 oxygen, H2O, add them up and you get the mass of a compound. So for salt, which is sodium chloride, we would take that mass of sodium, 22.98977, and then the mass of chlorine, 35.453, add them together and get 58.44277. That is the molar mass of sodium chloride. 1 mole of sodium chloride has a mass of 58.44277 grams. There's no unit on that number. It should be grams, okay? If we were doing sugar, sugar's actually a little bit more difficult. In sugar, there are 12 carbon atoms. Now, 12 carbon atoms, each of them has a mass of 12.011, 22 hydrogens, 11 oxygens, and we add up all of that and we get 342.2977 grams. That's the mass of 1 mole of sugar. Now, adding these things up in all these decimal places always brings up the question of where should we round this thing. And the truth is, if we wanted to do this with the right significant figures, we would have to be really careful about this, because remember that the adding rules are different than the multiplying rules, and since we're doing both adding and multiplying in a lot of these, it is just a lot of work. So way back in the day, in 2004, my very first year of teaching, we decided at Brilliant High School, when we have to add atoms to get a molar mass, we are going to round the result to 2 decimal places. 2. Count them, 2. And we are going to do that anytime we have to find the molar mass for a compound. Now, if I was working with something like carbon, I would just use 12.011. I wouldn't round it then because I can just get the number off the periodic table because it's an element. But whenever we're doing a compound and we have to add them up, we round it to 2 decimal places. Okay? So how does this end up working out? Looks like my animation's a little broken. So if we had a pound of sugar, okay? A pound of sugar, you kind of get a picture in your head. You know, maybe a 5-pound bag of sugar is maybe like this big. You buy it at the grocery store. So a pound is about 1/5 of that. A pound of sugar, how many moles of sugar is that? So I know that a pound is 454 grams. And so then I take that and divide it by that molar mass of sugar. We just found that out in the previous slide, which we found was 342.3 grams in 1 mole of sugar. The sugar grams of sugar cancel, and we're into moles of sugar. It's 1 1/3 moles. Okay, if we had 10 moles of salt, how much salt would that be? 10 moles of salt at 58.44 grams per mole. Again, we just found the mass of that in the previous slide, the 58.44, so back up if you need to see how we did that. That would be, it's going to end up being 584 grams, of salt. Okay, so that's the way we would do it if we were going from moles to mass or from mass to moles. Okay, now, so you can kind of add on to your chart here with this idea that changing moles into mass and mass into moles involves a fraction that has got the molar mass of the substance in it. Okay, and you just do the reciprocal. If you need to have the units be different, you just flip it over. Okay, if you're trying to cancel moles and go into mass, you want the moles to be on the bottom, and vice versa. If I'm trying to get out of mass and into moles, I'm going to put the molar mass on the bottom so that my grams cancel, and I'll be into moles then. This allows us to add on to your whole chart. So your whole chart is going to look a little bit like this, and this is really where we're going to leave off at the end of Chem 1, is with this being the end of the story for now, but there's a little foreshadow, dun dun dun, for now. Those of you who are going on to AP Chem are going to find that we make a little addition onto this thing. So if you wanted to show all of this stuff, it would look like this. I think it's actually easier and just as good to draw it like this. We use Avogadro's number to change particles into moles and moles into particles, and we use molar masses to change masses into moles and moles into mass. The way that fraction looks is based on which direction you're going, and what I would just remind you is to keep the units on all of the numbers and let the units guide you to put them in the correct place in the numerator or the denominator of a particular fraction. Okay, so actually I don't like necessarily showing it like this. I would rather do this and have you think consciously about that rather than looking at some diagram to always guide you through it. Okay, so if we want to now, we should be able to do 2-step calculations where we are going all the way from maybe one side of this thing, particles, into a mass, or from a mass into particles. That's going to be a 2-step calculation. And I'm sorry, apparently I didn't set up the animation correctly here. So we took a mass of a solid copper penny. That's what I was going to do tomorrow if I was here with you, and we were going to try and figure out how many atoms that was. So a typical penny might weigh 3.05 grams. And we know that copper atoms have a mass of 63.546 grams of a mole of copper. I got that off the periodic table. And I know that a mole of copper has got Avogadro's number of atoms in it. And so in the end, I get there's this many atoms, 2.88 times 10 to the 22nd copper atoms in 1 penny. This is why we use scientific notation. It is also why we use moles, is because the numbers are just unbelievable in chemistry. So what if we had a lot of carbon atoms, like a billion carbon atoms? You think of a billion as being a lot of carbon, right? A billion of anything is a lot of anything. If we had a billion carbon atoms, what would that weigh? So a billion carbon atoms, I wrote it out in scientific notation here, but you could write it out longhand. And I know that there is 6.02 times 10 to the 23rd of them in 1 mole. My carbon atoms cancel my carbon atoms. Now I'd be in moles of carbon, so I put the mole on the bottom here and go into the grams of carbon here. So again, we've gone across our mole map. We have gone from atoms of carbon into the middle, moles of carbon, and then going now into mass of carbon. The molar mass of carbon is 12.011. So a billion carbon atoms weighs 1.99 times 10 to the negative 14th grams, which is unimaginably small. I don't think that there's a balance anywhere around that you could put that mass onto and read it on a balance. There's no scale in the world that can do that. We can measure masses like that in other indirect ways, but that is an infinitesimal amount of carbon, and it's a billion atoms. Again, giving you an idea of both how small atoms and molecules are and how many of them there are in the world around us. Okay? Have a good weekend, guys. Your problem set is going to be due on Monday. It's problem set 7.3, I guess. Thanks. Have a good weekend.